Okay, so we're going to imagine a hypothetical study where we're going to draw a sample of 40 people. In a Monte Carlo study, you have to define a population model, and the model is always going to be statistical, right? So this is a hypothetical two-factor CFA. And, we've got all these things we defined. We've got this correlation between factor 1 and factor 2 set at 0.25. We've got all the factor loadings at 0.8. Each of the two factors has 5 indicators. What's not on here is we also have to eventually define is the variance of the errors of each of the indicators. So in a Monte Carlo study, we're going to draw many samples. And these samples are going to be generated by a computer based on this population model we're going to define. So we're going to draw many samples of the same size as our study, n of 40. And for each of these samples, often called replicates, we're going to perform our analysis and get parameter estimates. And then when we're done, we take an average of these parameter estimates across all the samples. And so these parameter estimates include whether or not something is significant, whether or not the confidence intervals covered the true value, which we know because we defined it in this population model, stuff like that. Right, so power is the proportion of the replicates where a test returns a significant result, independent of whether the estimate we got was good or not. And the difficult thing is that we only get an estimate of power from the sample we run the Monte Carlo experiment on. So we have to sort of do a little more work to find the right sample size to give us 0.8. So to make some guesses and keep iterating until we get the right answer. For something like this CFA, Mutane and Mutane, who are the people who write M+, have some guidelines for deciding on a sample size based on Monte Carlo study, and it's not just about the power; it's also about biases in the estimates, right? So we want our estimates in a CFA to be pretty close to the truth. So we always want less than 10% bias for any of the parameters in the model, even the ones we don't care about necessarily, and want the standard error bias for the parameter for which power is being assessed. So maybe those paths, right? We don't maybe care about the standard error bias for the correlations, or the standard error bias for the variance of the errors. We do care about the standard error bias for those paths if they are of interest to us. And we want our 95% confidence interval coverage to be somewhere between 0.91 and 0.98. And I'll show this all stuff when we'll get to it in a minute. And like I said, for the purposes of the simulation, everything in the model matters, not just the stuff we want power for. So at this point, I'm going to switch over to R. And I'm going to start running this lavaan two-factor thing. I'm just going to highlight the whole deal down to this part that says sim. And I'm going to start running it because it's going to take a while. So each of these is one of our 1,000 simulations. So while this is running, we're going to talk about that code. So this first section. How do I start from this slide? I don't know any of these buttons. Come on. I did that earlier. You gave me something totally different. That's fine. So, let's get this pen so I can do that. So, this first line is just describing F1 and its relationship to its 5 indicators. So, what this F1, so what's happening here is I'm assigning to this two-factor pop object this model in quotes. So the first line is just F1 is indicated by 0.8 times y1. So 0.8 is the factor loading. So 0.8 times y1, 0.8 plus 0.8 times y2, plus 0.8 times y3, plus 0.8 times y4, plus 0.8 times y5. So this is the population model, right? We're assuming that this is the truth, that indicators y1 through y5 load on F1 at 0.8. Similarly, for F2, y6 through y10 loads on factor 2 at 0.8. we're gonna it's just a guess. You might there might be some again some cutoffs people talk about it. What this is like a standardized factor loading. So it's not so this is standardized is the easiest thing to do because we just set all the variances of the factors to 1. You have to start thinking about what is the variance of a latent thing? I don't know. So these are all like standardized factor loadings where the variance of the factor set to 1, which you see right here. So these two, so like equals tilde is like a by statement in n plus. It implies like it's things that are indicated by f1 is indicated by these y1 through y5. This 2 tilde is a variance or a covariance. So when something covariance with itself, that is its variance. So the variance of f1 is going to be set to 1 times f1. The variance of f2 is also going to be set to 1. Just easy for this sort of standardized loading. And then we're going to assume that 0.25 is, it's this covariance that's listed. And I'm going to set the variance of all the indicators to 0.36, which indicates that the area variance is 0.36, which means that the proportion, the standard deviations is like 0.06, something like that. Pretty small, that's fine. So that's that first part. I think we're probably close to being done. Okay. And then if we look back at this R, I have to close that out. I just forget. So if we look back at R, this is our analysis model, right? All we're specifying is this sort of this chunk right here. We're specifying that, okay, F1 is going to be indicated by these 5 things. F2 is going to be indicated by these 5 things. And we're going to specify that, that the variances of the factors are set to 1. Otherwise, because of local identification, the first path would have to be set to 1 if we don't set the variance to 1. That's just a thing you have to do in a factor analysis model. And then down here, we've said in this 2-factor out, we've assigned it the output of this sim function. We've said we want 1,000 replicates, so we want to do this 1,000 times. The model we want to use, the analytic model, is this 2-factor analyze model that I created up here. We want an n of 40 in each sample, right? And then the generating model, the population model, is this 2-factor pop model that I set up here. And then this lavaan fun is just, there's 4 functions you can use in lavaan: CFA, SEM, lavaan, and something else. I can't remember what it is. Lavaan is the most flexible, but you have to set some more options. So this auto.var thing just means that lavaan is going to, from this specified variances and covariances, it's going to build a covariance matrix for you. This is the only way using the simsem to use these variances of 1. If you try and use the CFA bit, it won't work. It'll look wrong. Yeah, if you want to set the variances to 1. If you're okay with leaving that first path to be 1 and let the variance be whatever it is, but you have to build a population model like that, which is harder, I think. So all this auto-var does is it builds that covariance thing for you, and this auto-fix first thing equals false means that lavaan will not automatically set the first path for that factor to 1, because you've already said the variance is 1, so you've already fixed something that needs to be fixed. So that's what's going on there. So now we've seen that it's done the 1,000 replications, and we can get some summary stuff. So we call this summary function on this 2-factor out. It's going to spit some stuff out at us, a bunch of stuff, in fact. Some things you don't care about. I don't usually worry about this. I'm certain that it's, oh yeah, these are like the, this has to do with the imperial distribution of the fit indices. We're not going to worry about that. It's not that important. This is the meat of this stuff. which is kind of coming off the page. And then there's some other stuff here. But if we just want this middle chunk that we care about, you can call summary param on two-factor out, and it just gives you this middle piece. So for power, we've actually got, so this first column right here, I can do this first column is the average estimate. So how, like what, across these 1,000 replicates, what is the average of this F1 to Y1 path, the F2 to Y2 path, the F3 to Y3 path, which is like kind of interesting, not that important. We don't care that much about it. Well, I'll say why in a second. This is the standard deviation of those estimates, and it's not super important, but this is the empirical estimate of the standard deviation. So we have a standard deviation that we get from these formulas that we assume, and this is like this empirical, we've got like an empirical distribution. So we've got 1,000 replicates, and we can create a distribution from those 1,000 replicates, and the standard deviation of those replicates is 0.137. Can be useful. And because we can compare this estimated standard deviation from this distribution to the standard error that came out of the actual modeling software. Here's where power is. That's our big one, right? We can see that we've actually got kind of a lot of power for a lot of this stuff. So that's pretty good. I feel like I did something wrong here. No, I didn't. Okay. So power's good. So we know that we want above 0.8 for all this stuff. And then if we look at coverage, coverage is decent, except that we've got really bad coverage for a lot of these variance estimates, right? So our coverage is not really where we want it. And so we're not quite there, right? Our power is good, actually really good. Our coverage is not so great, is not awesome. Our biases are actually pretty good. So we want the absolute value of these average biases to be less than 0.05 for these factors right here, and they are indeed less than 0.05. And for these, we want less than 0.1. Yeah, 0.1. Those are pretty good. We don't have the standard error bias by default, and this little calculation right here will give us that. And really all that it does is it's going to, so this is like, this first column is like an empirical truth. We think that the real standard error is probably pretty close to this estimate of the standard deviation of the estimate. And this average standard error is the average of what's going to come out of the software if you run it one time, just as a guess. So the difference between this column and this column divided by this estimate is going to be like, so if we go back up, just find the right slide here. So this bias, this percent bias right here, that standard the standard deviation of the estimates is going to be very close to the true value for that standard error. And this average of the estimates from the models is going to be what your estimate is in this case. So if I subtract this column from this column and divide by this column, it's going to give me, or no, sorry, if I subtract this column from this column, if I subtract the second column from the third column and divide by the second column, it's going to give me proportionate biases. And so if I just run this, we can see that that it's pretty good actually. The proportionate biases for the standard errors is less than 10% in all cases and less than 5% in these samples. Man, I really feel like I've made an error here somewhere because that seems way too good. Let's try something. See if I was way down to 20. So in this case, we might be satisfied. But if we hadn't met all those criteria, if we hadn't got the biases that were less than 10%, if the coverage hadn't been, oh no, actually we're not quite there yet, right? Because the coverage for the variances was not quite good enough. So we said, okay, we're very close, but these coverages are not quite there. We'd like them to be a little bit better. We're very close, but we need to just get a little bit better. So let's go up to 50 from 40. So we did 40 before, so to 50, and see what that gets us. It'll take a second. I know this is like a little different. Do you have any questions about what's happening here so far? Well, I probably won't let this finish because it would take a long time. But what you see is essentially you run with a given sample size, you look at all those pieces, and if they're not quite good enough, you go up. If they're really bad, you probably go up by a lot. If they're pretty close but not quite there, you go up by the end by a little bit, and you just keep doing it until you arrive at something that gets you sort of above those cutoffs. And if you want to, you can like really, narrow in on like the exact n, but a round number is usually fine. If it's a round number that gets you just above those cutoffs, I think you can call it a day at that point. Unless you have a population that's like really hard to get access to, and like each one represents a lot of work, maybe then you go down to like the exact n you need, but I think usually that's not the case. So I'm gonna stop this one. And I've got one more Monte Carlo example to do. No, I doubt there are any dumb questions.
But so if we're doing this CFA, we need to find out more sample size for that.
Right.
And then what about our analysis?
I'm about to do a path analysis.
So if we're running both, we're doing both the CFA and path analysis.
I would use the one that's larger because you want to be powered for like the thing that is the least likely to. That's in the same way, in the same like minimum effect, right? You kind of got it backwards, right? Like it turns out that the thing with the smallest effect is the one that requires the largest n. So go with that. If you're doing more than one thing, go with that largest n. And you could actually do, if you're intending to do the CFA and the path analysis together, you could like combine them. I'm going to do them separately here, but it would be possible to do the whole thing as one piece.
Okay.
My path analysis is going to assume that it's all observed stuff, and I'm not going to care as much about a lot of these. In this path analysis, we're just going to do the power because it's sort of less. It's not, when you're not doing latent things, I don't think it's as important to make sure that you get all this stuff that fits together. Although you could still follow these things. Although what you get from manifest variables is a lot less than what you get from latent variables from simsem. So we can't get as much information. But I've got an example of a power analysis from dual mediators. So if we imagine that, right, you've got x, which predicts y, but it also predicts y through some mediator 1 and some mediator 2. I don't have a concrete example off the top of my head, but like this is sort of any situation where you've got two mediators and some other predictor that goes through those mediators and also goes directly to the outcome. So the things that we need to define are, and actually I'm going to pop over here and start this as well, because otherwise it might take a while. So I'm going to run this whole thing down to this sim line and let it run. So similarly, you're planning for 40. You've got all these relationships. So what you have to define is all the passive letters, right? So you have to define the relationship between x and y, the relationship between x and m1, and m1 and b1, and x and m2, and m2 and y. And you'll also be interested in estimating stuff that's not part of your population model, right? So when you do a mediation model, you care about that total effect through m1, the total effect through m2. So which is really like the total effect through m1 is a1 times b1, total effect through M2 is A2 times B2. And you might also care about the total effect of X on Y, which is going to be the total mediated effect A1 times B1 plus A2 times B2 plus C, right? So that we're, in this next piece, we're going to also estimate stuff that doesn't come from a population model. But we do kind of know what those values should be because we can calculate them from the population model. Literally, that mediated effect is going to be whatever the value of A1 is times the value of B1. That's implied by our population model, even if we haven't like explicitly defined it. Oh, okay. So here, right, I've defined this C. I can do this. So, oh God, I keep doing that. So here I've defined C. So the relationship between Y and X is C is going to set to 0.15, right? So this is C. M1 to X, which is this relationship right here, A1, I'm going to set to 0.4. And then M1 to Y, I'm going to set to 0.2, right? So 0.4, 0.2. M2 to Y, M2 to X, I'm going to set to 0.3. And M2 to Y, I'm going to set to 0.3 as well. So I'm setting these values here. Arbitrary. Okay. Ideally, you look in the literature for the relationships you hope for. And so we also have to set the residual values, like we did with the regression earlier. We have to have some sense of, so here, right, Y is going to be explained by M1, X, and M2. So ideally in the literature, you'd have some sense of like, in your final model, how much of the variability do you expect to explain in Y, right? And so that's going to be the Y, this double tilde, right? Y covariant with itself is, you're assuming that 0.6, which is, I hope, maybe not 60% of the variance here. This is, in the path model, it's harder to know if it's got the same standardized thing. But let's assume that the unexplained, the variance of the disturbance, the unexplained variability is 0.6. And similarly, to some sense of M1 and M2, what the value of these disturbances are going to be that we didn't sort of draw here, unexplained variability in them. I set them to 0.3 and 0.4. And then down here, I've done this sort of path model. And I gave them names, unlike earlier where I just said, in this model right here, where I just did this stuff without any names, this stuff without any names, in order to get some of the other stuff, I need to name these paths, right? So Y is predicted by C times X, and this value right here is just what that path is going to be called later on. And you'll see in the output. So I define Y is predicted, right, by all three of these things. Y is predicted by M1, by X, by M2. M1 is predicted by X. M2 is also predicted by X. So you just sort of look at like anything that is an arrow into that thing is predicted by that thing. It's like a bunch of regressions sort of put together. We also care about these indirect effects. Ooh, I should have just made this something else. That's fine. We're going to call this indirect effect communication mediation and some self-concept mediation, right? So this first path, this sort of total mediated effect is A1 times B1. This total mediated effect is A2 times B2. And then the total effect of X is going to be this C path plus these two mediating paths. And it's done again. So if I go down and I get the summary of the output, we get kind of a lot less. Let's run that again. So we still have power, but we don't get any of that coverage stuff. And I actually I'm not certain I get coverage out of this particular piece with no latent things. So I'm just not going to worry about it for the moment. But we see the power is really bad. especially for these small effects like C, which is only set to what 0.15, pretty small. B1, B2, not great. We might not care so much about the power of B1 and B2 because we maybe just care about the total mediated effect. But if we look down here, right, these individual mediated effects have also really terrible power. So we're not quite there yet. And we can, like I did earlier, get estimates of the biases. Whoops. First, these are the population values of those parameters in the order that they appear in the model. So C is 0.15, B1 is 0.4, B2 is 0.2. Oh, that's in the wrong order. I want B1 is going to be no, I think that's right. I think we're good. No, it's not. So B1 is 0.2 and B2 is 0.3. A1 is 0.4 and that's 0.3 and everything else should be right. So 0.6 is the disturbance term for that one. 0.3 is the disturbance term for that one. 0.3 is the disturbance term for that one. For this 0.08 right here, that is 0.4 times 0.2, right? So it becomes 0.08. This 0.09 is the lower one, which is 0.3. So if I look, let me just go back here. Nope, that's not what I want. So right, this total path right here is this 0.4 times this 0.2. Those are the population effects that I set. This total mediated path is 0.3 times 0.3, which is the total effect that I set here. So that's what 0.08 and 0.09 are. And then this C, the total effect of the outcome is C, which is 0.15 plus 0.08 plus 0.09. So I set that there. Those are the population values. I get the first column, which is the average estimate, minus the population values divided by the population values. I get estimates of the bias. And we can see in general, actually, the estimates of the bias are not too bad. 0.02, 0.03, 0.04. The Y variance is not great. That's 0.1. It's sort of in that range we talked about before, because we don't really care about the estimating the error variance that well. But our power is garbage, right? We saw that earlier. So we have to maybe go up to, I don't know, 80 and just run it again and see what happens. Yeah, you just have to write more stuff, basically. I mean, it's just the more things you have to estimate, right? So the higher sample size has to be. So that is mostly, like, I'm going to keep running this in the background. We can talk about it some more, but that's like most of the things I was going to talk about. So, like at this point, like I said, you keep adjusting your sample size upwards until you get the bias and coverage that you think are acceptable. Are there any questions about what I did? So, right, so just, things to take home. Power analysis is trial and error. There's sort of a lot of arbitrary pieces that go into power analysis, things you don't have control over. Become familiar with software, try it out, and also don't stress if you have trouble, because this is like the thing that we can help the most with, I hope, at Smarter. If you are interested in RCTs, I do have some material on that. I didn't cover it because it hasn't been a big interest in past power analyses or my consulting, and also Adam can help with RCT stuff if you're trying to do a grant kind of thing. So that is everything, unless there are more questions. Yeah.
Is optimal design the best thing for multi-level modeling?
Probably. Power Up might do it as well. What's that?
Are there any kind of simulations?
You can do simulation for multi-level stuff. I would say that if there is software that does it without simulation, that's always like, it's just easier than doing a simulation, less time consuming. But you can simulate any of this stuff. Like all the things we did with G-Power, you can also simulate that. It's just like not worth the pain to do it. So like if you really wanted to do, if you were like, man, I really don't like this F thing. I want to do my power analysis using this D that I found. Like I want to use an actual effect size that I recognize. You could do that with a simulation. But I couldn't just sit down and do it right now. I'd have to think about it pretty hard to make sure I got it right. And so, simulations, it's easier to make errors in a simulation than it is using like optimal design or G-Power. So in the cases where you can use software that exists, I think that that's probably advisable. But like if you have like a really complicated model, it's possible that optimal design might not do it. Again, Power Up is like an Excel-based one, and it works pretty well, I think. And it's got some RCT stuff in it, so that's also a thing to look at.
Does it have multi-level?